All right, so for this first session, I wanted to go over prime factorization because this is something that I refer to many times throughout the course. And it's taught in section 1 where you learn about fractions. But if you were like, oh, I don't remember how to do this, I need to review it, it's not obvious that that is the section where you would find it. So I thought I'll do just a whole separate video just on prime factorization because it is a skill that you need to refer to multiple times throughout the course, and it comes in handy. So in order to understand what this is, we have a lot of vocabulary that you need to understand. So first, we have factor or factors. We have these words. So these are numbers that divide evenly, which means there's no remainder, into another number. So let's say we have the number 10. So if we are looking for numbers that divide into 10, that gives us 1 divides into 10, 2 divides into 10, because 10 divided by 1, 10 divided by 2, these give you whole numbers. 5 goes into 10, and 10 goes into 10. So all of these numbers that I can divide into 10, these are called factors. So these are factors of 10, of the number 10. So it's just all the numbers that you can think of that divide into that number. So that's how I usually think of factors. But when we do prime factorization, we don't write it as like a division. We actually write it as multiplication. So another way to look at it are numbers that are multiplied together are factors of the resulting answer. So if you have something like 3 times 5, which I was about, gives you 15, not 16. 3 times 5 is 15. 3 and 5 are factors of 15 because you can multiply them together to get to 15. So you can think of it 2 ways, as numbers that divide into something, or numbers when you multiply them together create this number you're looking for. So just some other vocabulary. Product is what we call the result of multiplication. So the result of multiplication is product, but we can also call writing things as multiplied as a product. So that's another term that you'll see. But what's important here is understanding what factors are. Factors are always equal to or smaller than the number you're listing factors for. So notice that all of these numbers are basically smaller than the other number except for like 10. 10 is a factor of itself. But you don't have like 12 because 12 doesn't go into 10. It gives you a decimal if you try to divide that. So all of these numbers are smaller or equal to the number that we're looking, the big overall number. So the next thing that you need to understand are prime numbers, because prime factorization, we just talked about factors, now we need to talk about the prime part. So a prime number is a natural number, and natural numbers are just our numbers 1, 2, 3, and so on. So they're numbers we count with, but we don't include 0, because when we start counting, we don't count at 0, we start at 1. So it's just a natural number, but specifically greater than 1. So 1 is not a prime number. We don't consider 1. And it's a number that has only 2 factors. So there are only 2 numbers that divide into it. Basically, the only number that you can divide into it is 1, because 1 goes into everything, or itself. So some examples of prime numbers, the first few primes are 2. 2 is a prime number because it's only divisible by 1 and 2. 3 is prime. 4 is not, because 4 can be divided by 2. It can be divided by 1, and it can be divided by 4. So there's 3 numbers you can divide into 4. 5, 7, Now you may be thinking, oh, every odd number is prime, but that's not the case because 9 is not a prime number because you can divide 9 by 1, 3, and 9. So the next prime number is 11. We have 13, skips 15. We go to 17, 19, skips 21. We go to 23. So these are all prime numbers. And you really only need to know really these numbers. You don't really have to memorize the primes that are larger than this. If you know your multiplication tables, basically if you can do your multiplication tables up to 10 times 10, you know all the prime numbers under 100. Because if it's not in that multiplication table, it's basically a prime number. So that's a nice little thing, is if you know your times tables, you know your prime numbers. So these are what primes are. Now, prime factorization combines these two concepts. So we're doing prime factors. So we're basically taking a number and we're breaking it down into multiplication of primes. So we're breaking it down into multiplication. So we're factoring the number. So we're writing the number like in the right on green, where you multiply these things together. So we're going to write this number as a series of multiplications, but all of the numbers are going to be prime. So like 3 times 5 is a prime factorization because 3 and 5 are prime numbers, and they give us 15. So I'm not going to be writing a number with a number that's not a prime. Like I wouldn't write 10 as, no, 10's a bad example because those are also prime. Like 16, I wouldn't write 16 as 4 times 4 because 4 is not a prime number. So prime factorization, you're trying to break these numbers down so it's just a whole bunch of prime numbers multiplied together. And you can have more than 2. You could have 3, you could have 5, you can have a lot of them multiplied together. And the book shows 2 ways to do this. It shows a way of just dividing. I always do a factor tree. And so a factor tree is basically you start on top with the number that you're trying to break down into smaller pieces. And you say what 2 numbers multiply to that number. And then you create branches with those 2 numbers. And then you're like, okay, what numbers multiply to this number? And you just keep branching off until you get smaller and smaller numbers, and you have only prime numbers left. So it creates a tree because you just kind of have a whole bunch of branches going off. And then your answer is all of your prime numbers multiplied together. So your answer, it is a product of primes, which is just your resulting prime numbers multiplied together. Since product means multiplication, so we're multiplying primes. So I mentioned that this shows up. We're going to look at it several times during this class. So the reason why they teach it in the section with fractions is because you can use it for reducing or simplifying fractions. You can use it for multiplying or dividing fractions. You can use it for finding a common denominator. You can use it for finding the least common multiple of 2 numbers. You can use it for finding the greatest common factor. And you can use it for factoring. These last 2 things are going to be in the second half of the class. So that is basically going to be weeks 4 through week 6 is you're going to be doing that kind of thing. So the first half of the class will be doing more of the dealing with some fractions and things like that. And then weeks 4 through 6 will be factoring, finding the greatest common factor. And so this is going to show up again. That's that second half of the class. Now, in real life, prime numbers are super important. And prime numbers are used for a lot of things. And you may or may not have heard of the greatest, it's called GIMPS, Greatest Internet Mersenne Prime Search, I think is what it stands for. But they're basically looking for prime numbers, and we use computers to try to find the biggest prime number, and you're probably like, why are we bothering to find this? Well, prime numbers are used in cryptography. The larger the prime number, like the harder it is to break a code, basically. We try to, when we're trying to code things to encrypt them, we like to scramble it up by using prime numbers, and it's a lot harder to decode them by using prime numbers versus another number. And so the bigger the prime number that you can find, the harder it is to decode, because the harder it is to determine that it is prime. So that's very useful in cybersecurity. Harmonics, so there are some things where you're dealing with sound harmonics or even just resonance harmonics of like vibrations and things. Prime numbers show up there. LCD screens, the way that they do color intensity actually uses prime numbers. And even related to nature, cicadas, their life cycles are prime numbers. There's the, I think there's a 3-year cicada, there's a 7-year cicada, there's a 17-year cicada. Those are all prime numbers. So they basically reemerge on prime number after every prime number cycle, which is really interesting. And the way that computers try to find these prime numbers, especially the really big prime numbers, is by doing prime factorization. It's just trying to, it takes a really big number and it just goes through and tries to see, does this number divide into it? Does this number divide into it? And it just tries every single possible number it can. And there are some tricks to make it faster, but they're basically doing prime factorization to determine if something is prime or not. And you're just trying to split it up into smaller pieces. So before I go into any examples of this, are there any questions?
No, ma'am, not at the moment.
Okay. So I'm going to start with smaller numbers, and then we're just going to keep kind of get bigger. I'm going to start simple with 35. So we're going to find the prime factorization for these numbers. And so you're making a factor tree. You're basically trying to split, if I can get my pen to actually write. You're taking 35 and you're asking yourself, what two numbers multiply to 35? Which in this case, 7 and 5 multiply to 35, 7 times 5. And then you ask yourself, are these numbers prime numbers? So 7 is on our prime number list, so I like to circle them. And 5 is on the prime number list, and so I circle it when I find a prime number. And once you've circled every number and you can't break it down any further, that's when you're done. So this is just a one-step prime factorization. And so our prime factorization for 35 is 7 times 5, or usually we'll write the smaller number first. So we can write this as 5 times 7. So it seems kind of silly, like why would you do that for a small number like this? But it's more useful when you have larger numbers, because then you can kind of see what numbers you can divide out of it, especially if you're trying to reduce a fraction. So let's take 105. So immediately you probably don't know what numbers multiply to 105. But if your number ends in a 0 or a 5, 5 always goes into that number. So because it ends, the last digit is 5, I know I can divide 5 into this number. So I just have to figure out 5 times what gives me 105. So I just do the backwards. I do 105 divided by 5 to get me my other number, and that comes out to 21. So 5 is a prime number, so I'm going to circle that, but 21, we can split that out further, because 21 is 3 times 7. So I can split 21 up, and then I look and I'm like, okay, 3 is one of our prime numbers, so I'm going to circle that. 7 is a prime number, so I'm going to circle that. And now I've circled all of the bottom numbers, and so there's no more splitting that I can do. So our prime factorization if I start with a smaller number, I've got 3. And then the next one is 5. And then 7. So 3 times 5 times 7 will give us 105. So it's not too bad. The prime factorization here, by writing it this way, if you do this in a fraction on the top and the bottom, then you know what you can cancel out. Because you can see, oh, I have a 3 on top, a 3 on the bottom, and it makes simplifying and reducing fractions a lot easier. Few more here. These are also ones that end in 5 because that's just easy. I picked ones that end in a 0 or a 5 because I know that I can split them up. I know they're not prime. So we've got 110. So this can go either way. So 110, if I look at that, if it ends in a 0 like that, I know that I can multiply it by 10. Or because it's a 0 or a 5, if it's divisible, that means it's divisible by 5. So I can split this up multiple ways. I can split this up as like 10 times something, or I can split it up as 5 times something. And it doesn't matter which one you pick because you get the same answer in the end. So it really doesn't matter. I just do whatever comes to mind first. What is the first thing that I think of? And here I think of, oh, this is 11 times 10 to get to 110. So that is just where my mind goes. So that's how I'm going to split it up. 11 is a prime number, so I'm going to circle that. And then 10 is 2 times 5. And 2 and 5 are prime numbers. So our prime factorization is 2 times 5 times 11. Now on the right here, we've got 135. So here it ends in a 5, so I know I can divide 5 into it. So I'm going to just use my calculator, and that gives me 27. So 135 divided by 5 is 27. So that's that missing number there. So now I need to split up 27. So that's 3 times 9. So knowing your multiplication tables is really helpful here because it makes this process go quicker. 3 is a prime number. And I can split 9 up as 3 times 3. So I have lots of 3s here. I kept branching out until I kind of got to the bottom with these 3s. So the prime factorization is 3 times 3 times 3 times 5. And if it makes it easier, if you're kind of losing track, you can maybe like highlight it. So like, okay, that's 1, 3, 2, 3, 3, 3. So you can make sure that you've written them all down because there's multiples, and then you can do times 5. So another way that we can write this is to take all of those 3's that are multiplied together. We have 3 of them that are multiplied together, so we can write that as an exponent, and instead write it as 3 to the 3rd power times 5, because there's 3 3's multiplied together. Either one of these is fine. The top is easier when you're reducing fractions, but the bottom is more compact, and so that is easier in some other circumstances. But it really doesn't matter which way you write it. If you're doing a problem like this on the homework, it will kind of tell you wants you to use exponents or not by whether you have the exponent option when you're entering in your answer. Because, you know, when you enter in your answer, it gives you some options for fractions and things like that. So if there's the exponent option, that means that it wants you to write it as the exponent, if possible, basically. So 2 more examples here. I could do an infinite number of examples. Basically, you could just give me a random number and we could try to figure it out. Usually when people try to give me random numbers, they end up being prime because there are a lot of prime numbers out there. So I try not to do random numbers, but we totally could. But I'm going to just do these 2 more here. So 112. So if you have a number and it ends in an even number, like 2, 4, 6, or 8, or even 0, that means it's divisible by 2. So if it ends in any of those digits, you know that you can divide it by 2. So even if you're like, I don't know what numbers multiply to 112, you can say, well, I do know that I can divide it by 2 because it's an even number. And 2 is a prime. So you can just pick the first number that you can think of and then use your calculator to divide it by 2 to get the other number. So 112 divided by 2 is 56. So then 56, that is one of the numbers that I'm really bad at with multiplication because I get 54 and 56 confused all the time. But 56 is 8 times 7. So 7 is a prime number, so I'm going to circle that, but 8 I can split up. So that's 4 times 2. So 2 is a prime number, and I can split up 4 as 2 times 2. And then finally we're at the end. And your tree could look different based off of where you put the numbers, if you put it on the left versus the right, what numbers you use. But you always get to the same number at the end. So our prime factorization for 112, I'm counting how many 2's I have. 1, 2, 3, 4. So I could write this as 2 to the 4th power because I have 4 2's and then times 7. Or I could write all 4 of my 2's multiplied together and then times 7. But that does start to get pretty long once you have a lot more numbers there. So let's take a look at this 476. So it ends in a 6. That's an even number. I know I can divide it by 2. So I'm going to do 476 divided by 2. This gives me 238. That ends in an 8, which is an even number, so I can divide it by 2. And this is probably the longest way to do this, but I don't really know my multiplication of numbers. So this gives me 2, and then I have 119. Now, 119, I don't know what goes into that. I think it might be prime, but we need to check. So it doesn't end in a 0 or a 5, and it doesn't end in an even number, so I can't divide it by 2 and I can't divide it by 5. There are tricks to see if you can divide a number by 8 or divide a number by 3 or divide a number by 6 or by 9. So there are little tricks to kind of determine that. But otherwise, the other way to do it is just to brute force it to check every number that you can think of. Now, on your calculator, there's usually a square root button that looks sort of like this. And if you take the square root of this number that we're trying to split up, it's going to probably give you a decimal. So I'm actually going to move this down a little bit. So when I take this square root of 119, I get 10.9, and I get a whole bunch of decimal numbers. The whole number part there is 10. what this means is I only need to check the numbers 1 through 10, and if none of those numbers go into 119, that means it's prime. So I don't have to bother checking things larger than 10. It's a nice little trick here. It kind of narrows down the numbers that you're trying. So dividing by 1 isn't going to do anything because that's not a prime. So we're going to try 119 divided by 2. Well, I know that's not going to work because it's not even. So I try 119 divided by 3. And I got a decimal number, so I know that 3 doesn't go into it. So then I try 119 divided by 4. And if you get a decimal, then you skip that one. 119 divided by 5, I get a decimal. So I skip that. So then I divide by 6. That gives me a decimal in my calculator. Divide by 7. That actually gave me a whole number. So this means that 119 is not prime. I thought it was going to be prime, and it's not. So I can divide it by 7, and then that gave me 17 as the other number. 119 divided by 7 is 17. And 17 is on that list of prime numbers. I hope I wrote it on the list of primes. Double check. Yes, I didn't forget that one. So 17 is a prime number on that list. So that gets me to the end, and so that's our last prime. So our prime factorization here. So I can count. So first, if you want to write all the numbers, it's 2 times 2 times 7 times 17. Or I've got 2 2's multiplied together, and then it's multiplied by a 7, and then it's multiplied by a 17. So you can write that as 2 squared times 7 times 17. And then that's your prime factorization. And that will allow you, once you have fractions, to kind of reduce. And then really all you're going to be using it for the first half of the class is reducing fractions and dealing with fractions. But that second half of the class is going to be really important when we're factoring. So just keep this in mind. You might have to refresh and watch this video again when we get to that, because that will be in 4 or 5 weeks. And you're probably not going to necessarily remember. But for now, this is helpful for dealing with fractions to make them simpler because you can cancel things out. So do you have any questions?
No.
All right. So that was all the examples that I had for prime factorization.